Hello, my name is Jake Maier. My project is a home networked intrusion detection system built on a $60 Raspberry Pi. The core idea is, can a cheap, off-the-shelf computer provide meaningful security for a home network without any advanced configuration? Let's find out. Most home networks today have a lot of devices: TVs, smart speakers, thermostats, phones, laptops. Every one of these is a potential entry point for something malicious, and most homeowners just plug in their ISP-provided router, pick a Wi-Fi password, and never think about it again. That means they have zero visibility into what those devices are doing. A compromised device could be stealing your data, watching your cameras, or participating in a botnet, and you never really know. This is actually still an open research problem, and there are commercial devices that try to help you with this, but they are very expensive and most are tailored towards enterprise customers. That is what motivated the project. So where's the opportunity? Every single device on a network, every phone, every laptop, every smart litter box has to resolve domain names to reach the internet. That means the DNS server is a universal observation point. Every device talks to it. DNS traffic is also lightweight and easy to log. Pi-hole is a free open source tool that's already designed to run as a home DNS server for ad blocking. My insight was that those same logs that Pi-hole already collects can be analyzed to detect malicious behavior. Malicious devices leave a recognizable signature in their DNS queries, and that's what I'm going after. Here's what I actually built. I set up a Pi-hole on a Raspberry Pi 5. I paid $60 for it a year or two ago, and I won't get into the outrageous price one of those is going for these days, and pointed my real home network at it as the DNS server. I collected 2 days of baseline traffic to understand what normal looks like. Since I don't have actual malware on the network, at least I hope, I wrote Python scripts to simulate 4 different attack types. I built an independent detector for each type of threat. Then I combined them into a live daemon that runs continuously on the Pi and flags suspicious clients in real time. Finally, I evaluated how it worked. The first attack is a suspicious domain query attack. When a device gets compromised, it typically needs to reach out to attacker-controlled servers, domains that have never been seen on the network before. My simulation queried a bunch of randomly generated, selected unknown domains over 2 minutes. Detection is pretty straightforward for this. I maintain a list of known good domains from my own baseline that I collected, plus a top 10,000 list from a company called Trenko. If a client's queries are more than 30% novel domains, and it hit at least 5 novel domains during the evaluation period, it gets flagged. The second attack is DNS data exfiltration. This is actually a pretty clever attack. An attacker can steal your data by encoding it as base 64 and stuffing it into a DNS subdomain. Like, instead of querying google.com, a compromised device will query ew9one cnbhc3.evilserver.com. That's your password encoded in the subdomain. Detection uses Shannon entropy. A legitimate subdomain is typically short and structured. Exfiltration subdomains are long and look like random characters. I flag any client that sends multiple high entropy, long subdomain queries to the same base domain. The third attack that I looked for was query bursts. This is a denial of service style attack where a compromised device floods the DNS server with hundreds of queries in a few seconds to overwhelm it. My simulation fires 200 queries in rapid succession. Detection bends queries into 10-second windows and computes queries per second. Anything over 10 QPS gets flagged. It's a pretty simple attack, but effective and easy to detect. The fourth attack that I looked for is beaconing. This is when a compromised device will check in with its command and control server on a fixed schedule, like clockwork, every 30 seconds, same domain. My simulation does exactly that. Detection looks for domains queried repeatedly with very low jitter, meaning the time between requests is almost always exactly the same. A human that is browsing the web won't do that. Automated malware can query at that kind of fixed schedule. I require at least a 5-second interval to avoid confusing a burst of requests with beaconing. That was happening, and I solved that by adding that minimum. The 4 detectors can each run on any batch of queries, a full day, a few minutes, whatever, but I wanted live monitoring, so I wrapped them all into a systemd service on the Pi. Every 30 seconds, it pulls the Pi-hole database, pulls all the new queries, and maintains a 15-minute rolling window per client. On each of these polls, all 4 detectors are ran against every single active client. If something's flagged, it goes into a 10-minute cooldown so I don't spam the user with the same alert every 30 seconds. Alerts are written to a log file on the Pi with the timestamp, client IP, which detector fired, and the details. Here's what it looks like actually running. You can see the daemon polling, and when an attack fires, the alerts appear in the log within 30 seconds. You can see I detected suspicious attacks, beaconing attacks, burst attacks, all of them except for the exfiltration. This is just through regular use of my network. Here's the batch mode output, running all 4 detectors against a full day of queries. You get a per client breakdown, which detectors fired, what the thresholds were, and example domains. This is what I used for the evaluation. Client 192.168.1.229 is my laptop where I was running the simulations. And you can see the exfiltration being detected, and a lot of those actually fed into the suspicious reasoning and the burst of the 20 QPS there. The results on a full day of traffic were 76,000 queries from 23 different clients. 3 of the 4 attacks were detected. Burst, exfiltration, and suspicious domains all fired correctly. Beaconing did not. More on that in a second. The false positive rate was high though. 13 clients got flagged. Only 1 of them was running my attack scripts. Beaconing flagged NTP, Network Time Protocol clients, and Steam, both of which poll on a regular schedule for completely legitimate reasons. The suspicious domain detector caught work laptops and my own Pi installing Python packages for this project. The one bright spot was that exfiltration had 0 false positives, because real subdomain strings are structurally very different from base 64 encoded data. None of that was in my baseline data or in my test data from normal house network activity. The root cause across the board is that my detectors are purely threshold based. They don't actually look at the baseline to know what's normal for each device. Hardware was not a bottleneck at all. The Pi averaged 1.4% CPU across a full day, occasional spiking up to 38%. Memory never went above 8.6%. Disk was essentially flat. So a $60 Raspberry Pi 5 is massively overpowered for this workload. So meaningful DNS-based intrusion detection is achievable on cheap hardware. The math works, the detections work. The problem is the false positives. There are too many to be practical for a real homeowner who just start ignoring the alerts if this was their real system. The fix is to improve the detectors, make them baseline aware. Instead of asking, is this unusual in general, they need to be asking, is this unusual for this specific device? Because a laptop querying for new domains is normal, a smart litter box doing the same thing is not. I also want to revisit my beaconing simulator. It's the only one that did not get detected. I'm not sure what went wrong there. It's probably the most realistic real world attack. And finally, a notification system would be great. Instead of having to check the logs of the Raspberry Pi through SSH to find out if my toaster is spying on me, I would like to get a phone ping or a Discord message. Thank you very much. That is the conclusion of my project.